Hey everyone, welcome to our last lesson on chemical reactions. Today we're going to be talking about stoichiometry of equations. It's kind of a big word. It was on your vocab quiz and has to do with the mathematics of mole ratios. So by the end of today, you should be able to determine the number of moles of reactants and products needed in a chemical equation, otherwise known as stoichiometry. And in the little diagram here, we see that we need 2 hydrogen molecules for every oxygen molecule to make 2 water molecules. The stoichiometry has to do with, well, what if we wanted, let's say, 10 water molecules? How much hydrogen and oxygen would we need then? Well, stoichiometry is all about proportions. And I like to liken it to cooking, which I will share with you a story with you in a moment here. But the coefficients in front of a species in a chemical equation indicates the proportional number of moles of reactant that we need to make a proportional number of moles of products. So let's say you wanted to make eggs for your brothers and sisters, or pancakes for your brothers and sisters some Saturday. We know that you need, let's say you need 2 eggs, maybe 2 cups of pancake mix, a cup of milk, maybe a tablespoon of oil, a tablespoon of vanilla. We'll call that the recipe. We can make pancakes from that. It'll feed your brothers and sisters perfectly. But what if your parents decided that they wanted pancakes as well? Or maybe your aunts and uncles came over, grandparents came over, and now all of a sudden, instead of making pancakes for 3, now you have to make pancakes for 6. How would we go about getting enough ingredients to make a perfect number of pancakes so that everybody is satisfied? Well, we can use stoichiometry. And not only is it good for chemical reactions, chemical equations, but it's what is used in cooking all the time. We'll apply this to a process called the Haber process, which has to do with making ammonia. And we look at the reaction here, and I'll give you a second to think about what type of reaction this is. Feel free to pause the video. This is a synthesis reaction, reacting nitrogen and hydrogen to yield ammonia. Specifically, 1 mole of nitrogen reacting with 3 moles of hydrogen to yield 2 moles of ammonia. This is essentially our recipe to make ammonia. And the key here is the ratio, the 1:3:2 ratio to make the ammonia. And this is what we want to preserve when we apply any different types of changes that we're going to apply to this reaction. Now, stoichiometry is all about changing amounts. So instead of 2 moles of ammonia, what if we needed 10 moles of ammonia? So we want to make sure that we still preserve this 1:3:2 ratio. And what I'm going to do here is set this up in this way. So this kind of reads left to right, our 1:3:2 ratio. If we change that to, instead of having 2 moles of ammonia, what if we had 10? What do we have to do to our numbers here, x and y? How do we change those numbers to make sure that we get 10 moles of ammonia? What do we exactly have to do here? Well, to get from 2 to 10, all we did here was multiplied by 5. So if that's the change, then that's all we really need to do to get x and y. So we would multiply 1 times 5, and we'd multiply 3 times 5 to get us our proportional numbers. This would give us 5 to 15 to 10. So in order to get 10 moles of ammonia, we need 5 moles of nitrogen and 15 moles of hydrogen. If we divide each of these by a 5, what we get is a 1, 15 by 5 is 3, 10 by 5 is 2, which matches our original proportion from the Haber process reaction. So the key with stoichiometry is preserving your proportions from beginning to end. We're going to do this in a series of sample problems. Now, in your notes, there's an alternative way of doing this using dimensional analysis, which I tend to steer away from, and I like to do my stoichiometry with ratios. So I'm going to proceed with this lesson using ratios as opposed to dimensional analysis. If you'd like more information on using dimensional analysis, you can consult your notes or come see me for some additional information. So again, if we have our Haber process here, nitrogen gas plus hydrogen gas yields ammonia gas. How many moles of ammonia will be formed if 6 moles of N2 are completely reacted with H2? So completely reacted with H2 means that we're going to use all of this nitrogen up. And this is most likely going to be in excess. Kind of like if you think about it, you had, if a sandwich requires 2 pieces of bread and a piece of bologna, and you had 2 slices of bread and 2 slices of bologna, you would completely react the bread with the bologna and you'd be left with some additional bologna. In this case, the hydrogen is the bologna and the nitrogen is the bread. We're going to completely use up the bread. In this case, we'll completely use up the nitrogen. So we always need to start with the original ratio from our equation, which is 1 to 3 to 2, nitrogen to hydrogen to ammonia. Now, question's asking for, well, what if we formed, or what if we use 6 moles of nitrogen? So I'm going to say we have 6 here. And in order to get from a 1 to a 6, what we did was we multiplied by 6. So really what we're going to do is we're going to take this ratio and multiply it by 6. We'll multiply this across. 6 times 3 would give us 18, and 6 times 2 would give us 12. So we would need, or we would form 12 moles of ammonia gas by reacting 6 moles of nitrogen completely with hydrogen gas. Now, if we look at this simply in ratio form, if we compare the 2 species that are being talked about here, ammonia and nitrogen, the ratio there, I'm going to look at this from left to right, the ratio of nitrogen to ammonia is 1 to 2. Now, if we set this up as 1 to 2, this being our N2 and this being our ammonia, if we changed the N2 to 6, how much ammonia would we have? We could then cross multiply and X would come out to be 12 moles. So we can use ratios to determine what our new number of moles might be. Let's try that again. We'll stick with the same reaction. How many moles of H2 are needed to completely react with N2 to form 1,000 moles of ammonia? So again, we're going to start with our ratio here, 1 to 3 to 2, and we're talking about H2 to form NH3. The N2 is in here as excess because it's completely reacted with N2. We're going to use up all the H2. So what we want to do is look at the ratio of H2 to NH3. H2 to NH3 is a 3 to 2 ratio. Now if we set that equal to the change, keeping the same species on top and on bottom, if we now had 1,000 moles of NH3, how much H2 do we need? We cross multiply, we get 2x equals 3,000, divide by 2x equals 1,500. When we compare 2 to 3, 3 is 1.5 times bigger than 2 is. And if we do the same thing with the 1,000 moles, 1.5 times 1,000 would be 1,500 moles H2. So we're comparing our ratio before a change to the ratio after. We're applying that same proportionality from beginning to end. I kind of covered that up there. The second part here says how many grams. Let's see if I can. I'll erase this here for now so we can see this. It's my mistake for drawing on that. How many grams of H2 would be needed? So we know that we have 1,500 moles of H2. Now all we need here, we're going to look for a given mass. This is from table T. That's what we want. How many grams would be needed? As long as we know the gram form of the mass of H2, which would be 2 grams per mole. We cross multiply this, and the given mass, we'll call that X, would be equal to 3,000 grams of H2. So we can use our mole calculation equation to convert between moles and grams of a substance. Given this reaction, which is a single replacement reaction, how many moles of sodium are needed to make 4 moles of H2? Okay. So we want to look and compare here. How many moles of Na? We have sodium and we have H2 being brought up in our question here. The ratio is 2 to 2 to 2 to 1. 2 to 2 to 2 to 1. So we look at Na, so 2 moles Na will normally give us 1 mole of H2. Well, if we have 4 moles H2, how many moles of Na would we need? So what we'll do here is we'll cross multiply, and our X moles of Na is equal to 4 times 2, which would be 8. Which makes sense because twice as much sodium is required to make half the amount of hydrogen, and this is the case here as well. This would be 8 moles. How many grams of sodium would be needed? Well, glad you asked. We have 8 moles. We can find our given mass over the gram formula mass of sodium, which would be 23.0 grams per mole. We could cross multiply this, and we get 184 grams of sodium. Got a couple more for you here. For the reaction, 4 aluminum plus 3 oxygen yields 2 aluminum oxide. This is a synthesis reaction in a 4 to 3 to 2 ratio. How many moles of aluminum oxide will form if 6 moles of aluminum are completely reacted with O2? So the O2 is going to be in excess. And we are going to use all this up. So we're comparing aluminum with aluminum oxide. Those are the two that are going to be changing here. So from our original equation, we have 4 moles aluminum that would produce 2 moles Al2O3. We set that equal to the change. Well, now we have 6 moles of aluminum. Now how much aluminum oxide can we produce? We cross multiply here. And we get X equals 3 moles. So depending on how much aluminum we start with, we produce half as much aluminum oxide. So if we had 6 moles of aluminum, half of that would be the amount of aluminum oxide we could produce. So 3 moles Al2O3. How many grams of aluminum oxide will form? Well, since we know we have 3 moles, we can do a given mass over the gram formula mass. Which would be 160 grams per mole. We cross multiply here. And we get 480 grams of aluminum oxide. And for our last example here, sodium chloride plus lead nitrate yields sodium nitrate plus lead chloride. What type of reaction is this? This is a double replacement reaction, which produces a insoluble salt, lead chloride. How many moles of PbCl2 precipitate when 5 moles of lead nitrate are completely reacted with NaCl? Again, the NaCl's are excess, and we're getting this just from the wording. We'll use up all the lead nitrate. So our initial ratio here, 2 to 1 to 2 to 1. 2 to 1, 2 to 1. And we're looking at how many moles of lead chloride when we use up all the lead nitrate. So we're using lead nitrate and lead chloride. That is a simple 1-to-1 ratio. We'll put that 1 over 1. So if we have 5 moles of lead nitrate, how many moles PbCl2 would precipitate? We cross multiply here and we get 5 moles of lead chloride will precipitate, since they are reacted in a 1-to-1 ratio. At this point, you should be able to determine the number of moles of reactants and products needed in a chemical equation. This is called stoichiometry. I will have lots of practice to give you in class. Make sure you write down any questions that you have, and feel free to ask them and share them with us when we see you in class. Hope everyone has a wonderful day.